You know, we start with in our previous discussions, we have a two-dimensional coordinate plane. And we have an x-axis and a y-axis, and they are perpendicular to one another. And they're arranged like this, where the x-axis is horizontal, the y-axis is vertical. Well, when we introduce a three-dimensional coordinate system, we need a third axis. And it's kind of logical to think that that third axis would go through like this. You see, just come out of the middle of the origin right here. And the 0 point on this number line would be at the origin of the original coordinate plane. Well, actually, we're going to rearrange it a little bit, and there is some convenience in this rearrangement, and we'll see that convenience later. But the way that it's arranged is like this, and notice the way that it's illustrated. And by the way, the illustrations in your textbook are outstanding. They are much better than I can do on the board. But let me take a shot at an arrangement right here. Notice the z-axis is going up here, the y-axis is to the right, and the x-axis is sort of coming at us. Now, to illustrate a number line that's coming at us, the positive values are coming at us, the negative values are on the other side of the board. But to illustrate the idea, we have to draw that x-axis somehow. So it's kind of drawn like this. Now, it puts the whole system into a kind of perspective which is not oriented toward right angles. And that's what makes the whole study a little bit difficult, a little bit challenging. Now, I think it's important the way that we sort of look at these values that are in the ordered triplet here. Now, you know, when you have the coordinates of a point in our traditional coordinate plane, you can think of x values as being horizontal distances and y values as being vertical distances. Or you can think of x numbers, x values, as being distance from the y-axis. And that's kind of interesting. Now, let me just take a point here and show you what I'm talking about. Suppose I want the point 3,5, and it might be up here. The 3 can be thought of as distance from the distance from the y-axis. So it is a horizontal distance. It is a distance from the y-axis. The 5, a vertical distance, is the distance from the x-axis. Now, in a similar way, the numbers here can be thought of as distances from the various planes. So -2 is an x value, but it is the distance from the YZ plane. Now, think about that a second. An x of -2, that means we went back. We went sort of behind our origin 2 units. Okay, but the YZ plane is the plane of the chalkboard. So the -2 for x means 2 units, you see, from our YZ plane. So each of these can be thought of that way, as a distance from a plane. Dimensional situation is this. Now notice it's just here's our old distance formula, and we just extend it with the difference in z value squared for the distance formula in 3 space. All right, suppose we want to find the distance between these 2 points. All we do is pop in information. Now, generally, when you use a formula like this, you want to write it down first, and you could write it down like this. I've taken a little shortcut here because we are accustomed to thinking about delta x as being a difference in x values, and delta y as a difference in y values, and delta z as a difference in z values. Usually when we use this delta notation, we're talking about little tiny differences, but it doesn't make any difference. We can talk about some pretty big differences here. So the difference in x components, well, let's see, it's the difference between the 1 and the 2. So I'm using 2 minus 1. And then for the difference in y's, 4 minus 0. And the difference in z's, -3 minus 2. You see, and all of those differences are squared. So I've collected in these parentheses, and I get these values squaring and collecting. I find the distance to be the square root of 42. 3 space, it's a similar idea. It's an extension of that idea, actually. And the midpoint between 2 points in 3 space is found by taking the average x distance, you see, average y distance, average z distance for our ordered triplet. So it's add the x's, divide by 2, add the y's, divide by 2, add the z's, divide by 2. Now, let's go through a problem. And in fact, let's slide over here and let's do this. Let's find the midpoint between these two. You see, and to do it, all we do is apply our formula. And the general idea, the general concept involved in it is the way that you'll recall it. The general concept. And what is that general concept? Well, the midpoint is an ordered triplet, and it is the average x value in these two. And I can put average x value, average y value, average z value, or I can just say x sub 1 plus x sub 2 over 2. Average y value, y sub 1 plus y sub 2 over 2. And average z, that's z sub 1 plus z sub 2 over 2. And let's just plug and play. All right, add the x's, that's 1 and 2 over 2. Add the y's, 0 and 4 over 2. Add the z's, 2 and negative 3. 2 plus negative 3 means 2 minus 3 over 2. Let's see, 1 and 2, that's 3. 3 over 2, that's 1.5. Then 4 over 2 is 2. And 2 with negative 3 is negative 1. That's negative 1/2. So here then are the coordinates of the midpoint between those 2 points. It's a similar idea. It's an extension of that idea, actually. And the midpoint between 2 points in 3 space is found by taking the average x distance, you see, average y distance, average z distance for our ordered triplet. So it's add the x's, divide by 2, add the y's, divide by 2, add the z's, divide by 2. Now, let's go through a problem. And in fact, let's slide over here and let's do this. Let's find the midpoint between these two. You see, and to do it, all we do is apply our formula. And the general idea, the general concept involved in it is the way that you'll recall it. The general concept. And what is that general concept? Well, the midpoint is an ordered triplet, and it is the average x value in these two. And I can put average x value, average y value, average z value, or I can just say x sub 1 plus x sub 2 over 2. Average y value, y sub 1 plus y sub 2 over 2. And average z, that's z sub 1 plus z sub 2 over 2. And let's just plug and play. All right, add the x's, that's 1 and 2 over 2. Add the y's, 0 and 4 over 2. Add the z's, 2 and negative 3. 2 plus negative 3 means 2 minus 3 over 2. Let's see, 1 and 2, that's 3. 3 over 2, that's 1.5. Then 4 over 2 is 2. And 2 with negative 3 is negative 1. That's negative 1/2. So here then are the coordinates of the midpoint between those 2 points. From time to time, we'll be talking about a variety of three-dimensional figures. The first one we'll talk about here is the sphere. And we'll talk about the equation associated with a sphere. And it comes from the equation associated with a circle. Now remember that when the circles were developed and the equations for circles were developed, they were developed in terms of the distance formula. If we have a circle whose center is at 4, 3 and it has a particular radius, then you use the distance formula by thinking of the distance r, and the distance is between the center of the circle and a general point xy that is on the circle itself. The distance formula is this, and that distance is the distance r that we're talking about here. A difference in x's is the general x on the circle minus the x component for the center. And then the difference in y is the y coordinate on the circle and the y coordinate at the center. And then using this, we square on both sides to clear the radical, and we have r squared is equal to this plus this. And to generalize the thing further, this situation further, if we're thinking about a center at a general point hk, then we have an h here and a k here. So the center is at hk and the radius is r. This is the equation of a circle. Okay, now we just extend the idea for the equation for a sphere, and we extend it just utilizing another point in the process. into this other dimension, into this z dimension. So it's the distance is equal to, and we start with that distance formula, and then that evolves into a situation where we have an r squared here. The squaring clears the radical once again, and it's x minus h, y minus k, z minus l. And the center of the sphere is at HKL. You see, that's the idea, and the radius is r. Well, let's work a few problems. Suppose we have a sphere, and the center is located at 2, 4, 3. The radius is 3, and we want to write the equation in standard form. Now, the equation can take a lot of forms, but the standard form is the form that we just looked at. So we might begin with the skeleton of the equation in standard form and just fill in the information we know. And we know just about everything here. We have the HKL is up here, so H is replaced with 2, and K is replaced with 4, and L is replaced with 3. The radius is 3, so R is replaced with 3, and we would presumably, though, probably write this as the 3 squared is 9, and this is the equation that we're looking for. To set up the next problem, imagine that I have a basketball. Imagine that I'm holding a basketball, and I take this basketball and I lower it into a tub of water. And let's say that I just kind of push it a little bit into the tub of water to where it's just, maybe 1/4 submerged or something like that. Now imagine where, as the water meets the sphere, as the water meets the basketball, what kind of figure is formed? The intersection of the water with the basketball right at the surface of the water. You see, it's just a circle. It's just a circular path for the water. And that's what we're talking about in the next problem. And that path is called the trace. Now, we're thinking here about finding a trace in a particular plane associated with the graph of this sphere. Now, this sphere has a center at 3, 2, negative 4 identified here, and a radius of 5. And we want the XY trace. Now, that's the trace, sort of the intersection then of the sphere with the XY plane. That's what the XY trace is. And it's going to form a circle. So what's going to emerge here will be the equation for a circle for that XY trace. And all we do to identify a trace is to understand that for all of the values, the coordinates of points that lie on the XY plane, what are the characteristics of the coordinates of those points? Well, every one of those points that lies on the XY plane would have a Z component, a Z coordinate of 0. So the distance from the XY plane is 0 if we're on the XY plane. That's the idea. So the Z value is 0. So all we have to do is take the equation up here and replace the Z with 0, you see, and evaluate. Now that just causes us to change the value of the constant over here, and the Z term goes out. But we have 0 plus 4, 4 squared is 16. If I subtract 16 on both sides, I get 9 for the constant on the right. And these components stay the same. So the trace is a circle, and here is its equation. And the circle has a center at 3, 2, and it has a radius of 3. And we could think about the XZ trace, the trace or the sort of the imprint that this graph would make, this sphere would make in the XZ plane. You see the intersection of those two. Now think about that. In the XZ plane, the Y value would be 0. So all we would have to do is replace Y with 0 and evaluate in a way that is similar to this one.